the integral of that differential shear force, this summation of this differential shear force, because this section here composed of so many differential elements, and each element is subjected to this differential shear force. So if we're going to sum up all those differential shear forces, it gives us resisting the resisting force. This one. That's the summation of this. Okay. Now, the bending moment due to the load, because this is an equilibrium condition, we can use static equation summing up moments about the z-axis equal to zero. The bending moment due to the loading is equal to, and this resisting moment is equal to the integral of the moment of this force about the z-axis. Okay, so the moment of this differential axial force is sigma x times differential area multiplied by the moment arm y. So this is equal to integral sigma x times y dA times y dA. So this is equal to integral. Now this sigma x here is the same as this. So that the sigma x is equal to A over rho multiplied by y times y times the dA. Okay? And this E here is modulus of elasticity, which is constant. The value depends upon the type of material, and this rho is constant also. The radius of curvature is constant. So we can place all constants outside integral sign. So integral y squared times differential area. And the right side of the equation, so that m sub r, or the bending moment due to the load acting to the left of the section, is equal to the resisting moment is equal to A over rho. Integral y squared differential area is the product of the area and the square of the distance. So that gives us the moment of inertia. Moment of inertia I. You see that y here is measured from the neutral axis. So the integral y squared times differential area is the moment of inertia of this exploratory section with respect to the neutral axis, since the y distance is measured from the neutral axis. Okay, so this one here, so we have now m is equal to ei over rho, and going back to this equation, our E over rho is equal to sigma over y, so that in this equation here, we have this moment of inertia, no? So this is equal to E over rho times I, but our E over rho is equal to this, sigma over Y. So that the equation now becomes E over rho is E over rho is sigma over Y. Okay? So this is equal to sigma over Y times I. So solving for the stress, that will give us my over I. Now, in this form of equation, we call this as we call this as fracture formula. This is to find for the stress, to determine the stress at a fiber located y distance from the neutral axis. Okay? Are there any questions in this equation? Before I continue.
None so far, sir.
Okay, good. Thank you. From the ladies. Any questions from the ladies?
None, sir.
Okay, good. Si Faith naman ako nadunggan. What about the others?
Wala, sir. None po.
Clara. Okay, good. Okay, so we will now use this flexural stress formula. To find for the maximum flexural stress, so the maximum flexural stress is equal to MC over I, where C there is the vertical distance, from from the neutral axis, to the fiber, and this is the remotest fiber to the farthest fiber, or to the okay, I'll just write here, farthest fiber. So if we have, say, a rectangular section like this, our neutral axis passes through the centroid, and the value of C, because the neutral axis here is an axis of symmetry, the value of C, or the fiber that is the remotest or the farthest from neutral axis, is this fiber here. This fiber. This one. The uppermost fiber. So that is the fiber which is subjected to maximum shear stress, flexural stress. Also here, this is the fiber that is subjected to maximum flexural stress. So because neutral axis is axis of symmetry, then that distance C above neutral axis is also the distance below. So for this section, the maximum the maximum flexural stress occurs in the farthest fiber, in the uppermost fiber, also in the lowermost fiber. And since this section is symmetrical with respect to the neutral axis, so this distance is equal to this distance. Okay. Now another variation for flexural stress is this one. the flexural stress is equal to MC over I, and this is equal to M over I over C, where I over C is called as the section modulus. Section modulus. And the section modulus is denoted by S. Okay, section modulus S. So that the flexural stress, therefore, is equal to M over S. So this is another equation to remember. But if you know this, you can also derive this one from here, because I over C is S. Okay. Now, in this figure here, in this figure, we have here the section modulus for each of the geometric shape. For a rectangle, the section modulus is bx squared over 6. Now, take note that our section modulus is I over C, and for a rectangular section, the moment of inertia with respect to neutral axis is bh cubed over 12. And the volume C is the distance from the neutral axis to the farthest fiber. Okay, so again, this is an axis of symmetry. So this farthest fiber, that distance there to the farthest fiber is also same distance below this lowermost fiber from the neutral axis. So this distance is same as that distance. That is our C. This one here, this is our C. This is our C. Okay, so our C therefore is 1/2 of H. So by 2, 1, by 2, 6. We can cancel this. That becomes 2. So this is now bh squared over 6, which is this one. bh squared over 6. Okay. Now you can try to derive this section modulus for the other geometric shape, or the solid circle, whose radius is denoted by small letter r and whose diameter is denoted by small letter d. Using this equation for section modulus, where I is the moment of inertia of this circle with respect to its neutral axis, over the volume C. Now the volume C is the distance, the farthest distance, no, from the neutral axis to the farthest fiber. Also here, this is also C. And that C is R. Okay. So you can derive this. Also for the tube section, we have here the section modulus. And for triangle section, we have also this section modulus. But the value of C here, since neutral axis here is not an axis of symmetry, the value of C is the farthest distance from the neutral axis to the fiber, in this case to that vertex there. So that is 2/3 of h. So using this equation, where I is the moment of inertia of this triangular area with respect to its neutral axis, over the value of c, which is this distance here, it's 2/3 of h, you will arrive in this s equals bh squared over 24. Okay? Okay, so please, as what I have said, do not hesitate to interrupt if there are questions. So we proceed with this figure here, this one. Now, here is a portion of the beam, and this is the exploratory section. Our section here is a rectangular section. And this is the neutral axis. Okay. So this section is this section here, rectangular section. And the distribution of the flexural stress varies linearly. Okay. This one here, this is the flexural stress above the neutral axis, in which this upper part is subjected to compression because this portion here above the neutral axis, the fibers here are subjected to compression when the beam bends upward, when the beam has that concave upward. And this part here is subjected to tension. So the fibers here are subjected to tension. So you see that this is the area in tension, and from the neutral axis above is area in compression. So this is the width of the beam, and this is the depth of the beam denoted by h. So from the neutral axis to that uppermost fiber of the beam is 1/2 of h. From the neutral axis to the lowermost fiber is h over 2 also, since this is an axis of symmetry. Now, this is the distribution of the flexural stress. Compressive stress due to flexure, due to bending. In the uppermost fiber, it is subjected to this maximum flexural stress. And it is directed toward the section since it's compressive stress. It is acting toward the section. While below is tensile stress. So the lowermost fiber is subjected to maximum tensile stress due to bending action. And you see that the direction of the stress here is away from this section. So that means that it is a tensile stress. And this one here is the resultant compressive force of this triangular stress distribution, while this capital letter T is the resultant tensile force due to that tensile stress. Okay. Now the distance from the neutral axis to the centroid of this area is denoted by h, and that h is 2/3 of c. Okay. This is sorry, this is not h but k. This is k. This is k. You know, it looks like it's it is k. This one here is also k. Now, since this is an axis of symmetry, the compressive force here, the resultant compressive force is also equal to this. By summing up forces horizontal equal to 0, C is equal to T. And the distance between them is distance E. So this resultant force C is equal to it is equal to 1/2 of the maximum stress multiplied by the area. Since this is linear, the average stress is 1/2 of this maximum stress. Or you can get the area of this, that is 1/2 times sigma C times C. Okay, where C is h/2. So 1/2. So the value of C is equal to, it is equal to, you can solve for C by determining this area of the stress distribution. So 1/2 times sigma C multiplied by C, that distance there, where that is h/2, multiplied by B, the dimension perpendicular to this. Okay. So that is the value of C. Or C is equal to the average stress. And because this is linear, the average stress is 1/2 of this. And multiplied by the area. The area is this distance multiplied by the dimension perpendicular to this one, which is B, which is this one here. This is B. Okay. So it looks like if we do the 3D, it looks like this one here, something like this. Something like this. So that C there is it is acting right here, like that. So this is our B, and this is h/2, and this is our maximum stress. So our C therefore is the average of that maximum stress multiplied by the area, which is B times h/2. So that is why we have now this. Okay, and this C is equal to T also, since this is symmetrical. No? And if this is E, our E here is 2 times this distance. So we have now our moment. This is resisting moment in that direction. That's a resisting moment. Is equal to the magnitude of the couple. Is equal to 1/2 times sigma times B h/2 multiplied by the distance E. Okay, that distance there, distance E. Okay, and that distance E is equal to this plus this, where this one here is 2/3 of 2/3 of h/2. Okay, this one here is h/2, and this is 2/3 of h/2. Okay, so this is 2/3 of h/2, while this below here is 2/3 of h/2. So our distance E is 2/3 h over 2 multiplied by 2. So this gives us 2/3 of h. That is our E distance. Okay. So I guess there are no questions since there is no interruption. So we proceed with this one here. This is a sample problem about solving for the maximum flexural stress. Could you please read this problem, volunteer?
Um, a beam 150 millimeter wide by
Mm.
250 millimeter deep supports
Mm.
the loads shown in the figure.
Mm.
Determine the maximum flexural stress.
Stress. Okay. Thank you. So to find for the maximum flexural stress, we uh, we determine the maximum moment, no? So maximum. So ano naman siya? Maximum moment. Hmm? Maximum moment is equal to, you're going to find for this because our maximum flexural stress is equal to the maximum moment times C over I. So to find for the maximum moment, we drew the shear diagram. So this is now the shear diagram. I presume that you know how to draw the shear diagram. The maximum moment occurs right at zero shear, right here. Okay, right under this concentrated load. If you project this vertically up. And the moment, if we project this vertically up, this is the section where we have the zero shear. So you are going to find for the moment right at that section where we have zero shear. So the moment at that section is equal to the summation of moments considering the left. You can consider this equation, or if I'll call this section A, that section there, and that section I call it C, that section there I call it B. So the moment at C is equal to the moment at A plus the change of the moment, no? So the moment at A is zero, okay, plus the area of the shear, plus the area of the shear from A to C. So what is the area of the shear from A to C? This area. And what is this area? It is the area of the trapezoid. So this will be equal to 0 plus area of trapezoid, 14 plus 2 all over 2 times 2. This gives us, this will cancel, so we will get here 16 kilonewton meters. That is now the maximum moment. So, maximum stress, therefore, is equal to 16 times 10 cube. Multiply this by C. Now, the value of C is from the neutral axis. From the neutral axis to the farthest fiber. Okay? And since it is symmetrical, so that is also C. And that is 1/2 of 250. So in meter, uh, 0.12 meters divided by 2. Oh, no, 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 no. 0.12. That's already one half. Oh, this one here. C. The value of C is, I'll just use black so that you can see it well. Value of C is one half of 250. That's 0.25 divided by 2 over I. Value of I is base times the height cube over 12. So that is how to determine our stress, the maximum flexural stress. Okay. Or you can use this equation here that the stress is equal to M over S, M over the section modulus B squared over 6. Or this is equal to 6M over BH squared. And you will get the same answer. And you will get the same answer. Now, the answer for that is 10.24 mega Pascal. This is times 10 to the power 6 newtons per square meter, or 10.24 mega Pascal. That is now our stress, maximum flexural stress. Okay. Hmm. Saan na siya? Hindi na siya mamove. Okay, so we proceed to this part. Um, this one here. This is another example. I supposed to assign this to somebody to present this to us, but since next meeting is our exam, pre-final exam, then I'll just discuss this to you. Could you please read, volunteer to read from the ladies? Volunteer? Nga ba yung ladies na to diri? Okay.
A timber beam 4 inches wide by 12 inches high and 20 feet long carries the loading shown in the figure. If
Okay.
the maximum flexure stress is 1,200 psi, for what maximum value of W will the shear be 0 under P, and what is the value of P?
Okay. This is W sub O, no? That's the intensity. The intensity of this uniformly distributed loading. Now, this is a simply supported beam. And in this problem, we want to know what is the maximum value of W sub O with the condition that the shear be 0 under P. Okay, in here. The shear will be 0 right here. So we have now this point 0 shear when we draw the shear diagram, and also this continuation of the shear diagram. Now, we first solve for the reaction R sub 1. Solving for the reaction R sub 1, this is 10, R sub 1 is 10 W sub O plus P over 4. P over 4. So this R sub 1 is determined by summing up moments about R sub 2 equal to 0. Okay. So we have here the shear diagram, and the shear at this section, at the left section is this 10 W sub O plus P over 4. Okay. Now, do not consider that first, because you will be confused with that. So the magnitude of the shear here is equal to this one. So I do not consider that first. Okay. And then we have this resultant. What answer the ink ning ko ano? Consider this part here to the left. We have this resultant force, which is equal to 15 multiplied by W sub O. So 10 W sub O plus P over 4 minus 15 W sub O is equal to 0. Okay, so the shear at this section here, if I'll call that section C, the shear at C equals summation forces vertical concerning the left. Since we are given that the shear under the load P is 0 from here. So the shear at C is 0. So summing of forces vertical to the left, we have that force minus that. So gives us 0 here. So we have now 10 W sub O plus P over 4 minus 15 W sub O is equal to 0. So that is why we have 10 W sub O plus P over 4 is equal to 15 W sub O, which is this one here. Okay. Now, what is the maximum moment? The maximum moment occurs at 0 shear in here. It will occur at 0 shear. So you find for the moment right here at this section. Okay, so the moment at that section, which is our maximum moment, is just write script C. You sum up moments considering the left portion of the section. Gamay ng ink ni. So that is equal to 0 plus the area of the shear. And the area of the shear, that's from that section to that section, which is this area here. So this is equal to 0. Is equal to 0 plus positive area, 1/2 times 15 times 10 W sub O plus P over 4. And so this is equal to 1/2 times 15. Now this 10 W sub O plus P over 4, that is equal to this one here. So 15 W sub O. Okay. So from the moment flexural stress formula, we have the flexural stress, maximum flexural stress is equal to MC over I. No? So this is now equal to this, since this is the maximum moment. That is a maximum moment that occurs right at this point, at C, no? Right here, at zero shear. Okay, so this will now be 7.5. That's 15 over 2 times 15 W sub O times the value of C. Now the value of C here is the value of C is 1/2 of 12. Okay, so 1/2 of 12 over I. Now our I here is moment of inertia with respect to neutral axis. So that is BH cubed over 12. Okay, the base is our base is 4, height is 12. So this will now be BH cubed over 12. Okay. Now our maximum flexural stress is 1,200 psi. This is the allowable flexural stress, 1,200 psi. So we equate this to 1,200 pounds per square inch. Now take note of the unit. That's pounds per square inch. Now our moment here is foot pounds, since our unit for W sub O is pounds per foot. So therefore, this will be in foot pounds. Now, we multiply this by 12. Okay? This one here, we multiply this by 12 because this is in foot pounds. So I still have to multiply this by 12. Okay, so by 12, multiplied by 12. And now we have only W sub O as our unknown. You can now solve for W sub O. Our W sub O here is, this is equal to 85.3 pounds per foot. And knowing W sub O, you can solve for P from this relation here. Okay? You have here an equation with two unknowns, W sub O and P. So you can solve for P, knowing W sub O. Our P is 1,706 pounds. Okay? So that is how to solve the problem. If there are no questions, we proceed to the next. So we have 85.3 pounds per foot, no, for W sub O. It's just this one here. So please be careful of the units. Okay, so We now proceed with this one here. Economic sections. Now, in economic sections, we are going to select a section where it is economical, no? The most economic section. Now, for this case here, for rectangular section, this part here is under stress. Okay, you see that this part has lesser stress, this part. And also here, it is under stress. So to make this section efficient, what we do is we design this such that we have a bigger area here. So this part here will be placed in the upper part. Since this lower is under stress and this upper is it is subjected to that stress which is not under stress. So what we do to make it efficient to carry the stress, we are going to place this area in the upper part. Also, this we place it in the lower part. So we have now this section here. Okay. Now, it's not practical that we have this kind of section. So we need to join this too. So that is why we have now this middle part, which we call this as the weave section. This is the weave section. This part here, that part is called as the weave, while that part there is called as the plans. Also, this lower part here is also the plans. So that is why we call this as a wide flange section. So to make this efficient, to carry the stress, I repeat, in this section, this part is under stress. Also here. So to make it efficient, we design it such that we have an area in here that carries the stress. Also, this part here is placed in the lower part, which is now this one. But these two is not joined, so we are going to join it with as a weave. Okay, so that's why we call this as a wide flange section or W shape. Now, in any of textbooks about mechanics of deformable bodies, in the last pages, you can see appendix, and in that appendix, you have there the list of sections. Okay. Now this is called as I-beam, or we call this as is shape. Okay, this is a section, and if you notice in a hardware, you can see this structural section, no? The steel section. This wide flange section is good for a column or a post. Okay. But this wide flange section is more efficient than the I-beam or the is shape. So, so here it says that for this section, rectangular section, a large portion of the cross section is under stress. So this part here is under stress. This part is under stress. So this makes it inefficient for resisting flexure. Because in our formula, flexural stress is, in our formula, we have the flexural stress equals MC over I. So the lesser your I, the greater is this stress. So so with this arrangement of the section, the moment of inertia would greatly increase, resulting to a greater resisting moment. Okay. Now, I'm going to give you a sample problem about economic section. By the way, these are the list of the list of the list of the wide plans section. This one here. This is found in the appendix. So you see here we have in the first column we have designation W. This is a wide flange section. W 920 by 446. This 920, this refers to the depth. The depth. If this is the wide flange section, the 920 here refers to the depth. This depth, and this is in millimeters. Okay, so this is just a designation. Now, actually, the depth is this one, 933 mm, if you are going to measure it. But the designation is only W920 by 446. Okay, you see, you have here the depth, 933 mm. Now, this second number here, this refers to the mass per unit length. This is 446 kilograms per meter. And this is just a designation, and the actual theoretical mass is given here, 447.2 kilograms per meter. Okay, so this refers to the depth, and this refers to the mass per meter length, per linear meter. And we have here the cross-sectional area given, and plans width. The plans width here is this. That is the plans width. The thickness of the plants is this thickness. Okay, weave thickness. The weave thickness is this thickness here. That's the weave thickness. And with respect to this axis, XX, you have here the moment of inertia. And this is the section modulus, I over C. This is 10 to the power 3 millimeters cube. Hindi nakaklaro. This is radius of gyration, and this one here is the moment of inertia with respect to the y-axis. Okay. So these are the lists of the properties of wide flange section. Okay, you have it also here. So from this list, we are going to select the lightest or the economic section from the list. Refer to this list in the appendix. Now, in the exam, I will give you the list, maybe only three sections, and you're going to select. So I'm going to give you the properties of those sections. So you don't need to refer to this appendix. So how do we use this one? Okay, to apply this table, we consider this sample problem. We'll try to solve this sample problem. This is posted in the canvas. This is, by the way, made by our chair, Engineer Fornis. You please read the problem. Volunteer to read. Why mo volunteer? Ano mo kabog? 62.
Ako lang, sir.
Okay.
A simply supported beam, 10 meters long, carries a uniformly distributed load of 20 kilonewton per meter over its entire length and a concentrated load of 40 kilonewton at midspan. If the allowable bending stress is 120 megapascal, determine the lightest weight shape that can be used.
Okay, thank you. Determine the lightest W shape. This means that we have wide flange section shape, W shape. So this 40 kN is located 5 meters from either of the ends, since this is acting at the midspan. Now, you are required to determine the lightest W shape that can be used. Okay. So how do we determine this lightest W shape? Now, to solve this problem, what we do here is we first solve for the reactions. Okay, solving for the left reaction and the right reaction. Since this is symmetrical, the loading is symmetrical, then the left reaction must be equal to the right reaction. It will be equal to 1/2 of the total load. Okay. So the total load now is, what's the total load? It will be solving for the total load. This will now be equal to, we have here the resultant of the uniform distributed load acting also at the center. So that this will be 20 times 10 gives us 200 kN. Okay, 200 kN. So 200 plus 40 is 240. 1/2 of 240 is 120 kN. Okay. Okay, so after we solve for the reactions, we are going to find the maximum moment due to the loading. So how do you solve for the maximum moment due to the loading? Where do you think is the location of the section where we have the maximum moment? It will be located at the center because it is symmetrical. No, you can verify that by constructing the shear moment diagrams. We will try constructing the shear moment diagrams. We'll try to find out. I'll just place it here. Okay, so we indicate the sections where we have the change of loading condition, and draw we draw vertical lines. We just use a ruler to make it straight. Mhm. Okay, now we make horizontal line representing zero magnitude of our shear. So this will be our zero shear. No? The unit is in kN. Okay, now, so we start with the shear at A. We have 120 because of that reaction going up. And 120 minus that resultant of that portion of the uniformly distributed load. This is 5 meters. That one there is also 5. So, so this part here, it has a resultant of that portion equal to 5 times 20. Okay, 5 times 20. Ano ni? Anti-crop. So 5 times 20, 5 times 20 is 100 going down, no? 100 going down. So 120 minus 100 gives us 20. Gives us 20. Then 20 minus 40 gives us negative 20. And negative 20 minus this resultant of this portion here. Okay, that resultant is also 5 times 20 is 100. So negative 20 minus 100 gives us negative 120. So we have this one, negative 120. And negative 120 plus 120 gives us 0. So we now connect the points. We have now this, and we have now this one. Okay. So you see that our shear 0 is in here, right at the center. So the maximum moment occurs therefore at the center. And that maximum moment is equal to is equal to the is equal to the moment at C. Okay. So the moment at C equals to the moment at A plus the change of the moment. So the moment at A is 0 plus area of shear from A to C. So what is the area of the shear from A to C? It is equal to this area of a trapezoid, area of that trapezoid. Done. So this is now 0 plus 120 plus 20 over 2 multiplied by 5, right? Try to check, huh? Oh, maximum moment, therefore, is equal to, how much this? Please compute calculator. What is now our maximum moment? Do you have your calculator with you? 120 plus 20, 140, 70. 70 times 5, 350, right? Is it correct?
Yes, sir.
Okay, thank you. 350 kN meters. Okay, so we know now the maximum moment. Now, this maximum moment here is due to the loading, due to the load. Okay, and this load is live load. This load is live load. Okay, so we will try solving uh, for for section modulus. Section modulus is equal to, what is that section modulus again? I over C, right? Okay, from the equation, the flexural stress is equal to M over S. And our allowable stress, flexural stress, is given here. That is, the allowable bending stress is 120 megapascals. So this will be 120 times 10 to the power 6 is equal to that 350 times 10 cube over S. So solving for S, this is the section modulus or the required section modulus for live load, because this is due to live load, due to the loading, due to live load. So this loading here is live load. This one carries a uniform distributed load and a concentrated load. So all of these are live loads. So the maximum moment here that we have just computed is the moment due to live load. And solving for the section modulus, the required section modulus for this will be, we use this equation here, that the flexural stress equals M over S. And this is equal to the allowable flexural stress, is equal to that maximum moment, 350 times 10 cubed due to the live load, over S. So this S here is the required section modulus for live load. And that will be equal to how much? That will be equal to, calculator please, 350 times 10 cubed.
2.92.
How much that?
2.92 times
2.92 times 10 to negative 3.
3. Yes.
So, yes, 2.92 times 10 to negative 3. What is the unit? Cubic meters. Okay, cubic meters, because this is section modulus is I over C. Section modulus is I over C. And this I, it has a unit in meters to the port. And our C here is the distance, that's M. Okay, I over C, that is section modulus. So this will cancel, that becomes 3. So you have now cubic meters. Now, we convert that to millimeters cube. To convert that to millimeters cube, multiply 2.92 times 10 negative 3. Multiply this by 1,000 cube. That will cancel. So this gives us, how was that? 2.92 times 10 negative 3 times 1,000 cube. That gives us 920 times 10 cube. 920 times 10 cube. Millimeters cube. Is it correct?
Yes, sir.
Right. Okay, thank you. Okay, so that is now the required section modulus for live load. So with this, you're going to select now the lightest W shape section. Okay. So refer to this one here. Section modulus here. This is 3,500 times 10 cube. Okay. What is our answer again here? This is 2,920, no? Times 10 cube. So 2,920 times 10 cube. Section modulus. 2,920. We select this, you see this one here, W690 by 125. This 125 is the mass per unit length. So 125 kilograms per meter. The depth of the wide flange section is 690 mm. This is just a designation. Actual depth is 678. Now, this has a section modulus of 3,500, but our computed section modulus is 2,920. Okay. So we need to select a wide flange section that has greater than this, 2,920 times 10 cube. So this one here is, you see that we have 3,500 here. This is greater than our computed section modulus. Now, this one here, this is 3,220. Napay mas nearer sa atong computed value, no? Computed value here is 2,920 times 10 cubic millimeters. Now, in here, we have 3,220 section modulus. This is 10 millimeters cube. We have 3,220. This is greater than our computed value. And this one here is 125 kilograms per meter. So this has a shorter depth. And but here we have the same mass per unit length. Now, since we select the economic section, then we choose this 610, the depth of 610 by 125. Okay, so we have now this. Try 610 by 125. So as we try 610 by 125, we solve now for the maximum moment due to the weight due to the weight. This is the dead weight. No, this is the weight of that section. So the weight is equal to 125.1 kilograms per meter. And converting this to newtons per meter, we multiply this by 9.81. Okay. So it gives us 1,227 newtons per meter. And with this, this is considered as uniformly distributed load all throughout the length of the beam because it's the weight of the beam, the weight of that chosen designation, W16 by 125. So we solve for the moment due to the dead load. The moment due to the dead load is, if you solve for that moment due to the dead load, okay, we have here, if we have this beam, we have this reaction here, and we have this intensity of the load. This one, uniform distributed load, and this is say W in newtons per meter, and we have this length L, and we solve for the maximum moment there. In this case, this has a load that is symmetrical with respect to center line because this is uniformly distributed load. Our R1 here is WL over 2, right? Because our resultant force here is equal to the area of the loading. So that is equal to the area of the loading is, that is the resultant, which is L times W, WL. So the maximum moment occurs right here. No? If we are going to draw the shear diagram, we have this WL over 2 and minus that resultant, the portion of that uniformly distributed load. This is L over 2 times W. So WL over 2, WL over 2 minus WL over 2 gives us 0. So we have now 0 here. And this is now the, something like this, no? The shear diagram. This is 0 here, somewhere here. I'll just throw it clearly. Something like this. Okay, assuming that this is so this point here is WL over 2. No? And this point here is also WL over 2. This is negative. So the maximum moment here, due to this dead load, is this is maximum moment due to the dead load is equal to 1/2 times L over 2 times WL over 2. Okay, so this is WL squared over 8. Now you see that in here, you have WL squared over 8. This one. Okay. Our W here is equal to this. 1,207 newtons per meter. The length is 10 squared over 8. This is now the moment due to the dead load. And the required section modulus due to dead load is M over stress, where M here is the moment over the allowable stress, which is 120. It gives us this one, 127.812 times 10 cube millimeters cube. So the total section modulus is the sum of those two. That section modulus due to the load and the section modulus due to live load. Due to live load, section modulus is this one. Okay? 2920 times 10 cube. Okay, so here you have 2916 times 10 cube. That is 2920 times 10 cube plus 127.8 times 10 cube. So it gives us this, which is, if you are going to compare this value with the section modulus in our selected section, this is our selected section, 610 by 125. Section modulus is this one, 3220 times 10 cube. That is for this designation. This is the section modulus. So that if you're going to compare it with this total section modulus, this is less than our section modulus of that selected section. It is this one. So therefore, okay, so yeah. So therefore, use this W610 by 125 for the beam. Okay. So that is selecting economic section. Are there any questions in here or portions which you cannot understand?
Excuse me, sir.
Yes.
Kanang unsay difference sa live load ug sa dead load?
The live load is a load that can be transferred, like the load of the people that is acting over a beam. Okay, that is live load. Also, another live load is the load due to the furnitures, or due to perhaps a book stand. Okay, the load that can be transferred. Okay, that is live load. But dead load, that is the load due to the weight of the beam. That is permanent, no? Weight. While live load can be transferred from one point to another point. We can have a live load that is assumed to be uniformly distributed load, something like this in our example. This example here. This one. This is considered as a live load. Okay, so if you have in the problem a load that carries that kind of that loading, that is considered as live load, and you're going to select a section, and with that selected section you are going to compute for the maximum moment due to the dead load, due to that weight. Okay.
Okay, thank you, sir.
Welcome. Any more questions? Time check is 8:56. So our coverage for exam will be up to here. Economic section. Starting from definition of share and moment. So one problem will be writing share and moment equations. second problem will be constructing shear and moment diagrams. I might give you a shear diagram and you're going to construct the load diagram as well as the moment diagram. Or I might give you moment diagram and you're going to supply the load diagram and the shear diagram. So that is about constructing shear and moment diagrams. You don't need to write the shear moment equations. Only the skits with those values of the shear and the moment at sections where we have the change of loading condition. So that's the second problem. No? In the third problem, I'm going to give you a problem about moving loads. Okay. Now the fourth problem is solving or application of the flexural stress formula or the bending stress formula. The fifth problem will be economic section. Okay, so there will be 5 problems, good for 2 hours only. That will be given next week on Tuesday. Okay? So I guess there are no more questions. I'm going to stop my presentation now. Before I will stop, are there any further questions before we will end this meeting?
None so far, sir.
Good. What about others?
Wala na sir.
Okay. And what about the lady?